Hello, everyone. My name is Mitali Banerjee. I'm from Laboratory of Quantum Physics, where we study strongly correlated electrons in topological phases of matter. These topological phases of matter are some exotic phases where they protect the properties from any local perturbation, disorder, etc., etc. And in this kind of systems, electrons are found to be in general strongly correlated, namely they interact with each other and you cannot anymore consider them as free electrons. So where do we find these kind of systems? We generally work in two-dimensional electron system where the electrons are bound to work, move around in a 2D material. And our main 2D material that we work in the lab with is graphene. Other than that, there is insulating material like hexagonal boron nitride, and there are plenty of other insulator or semiconducting materials, or even with exotic properties like superconductor, ferromagnetism, etc., can be found in these materials. Not only that, these materials are ideally two-dimensional, where the electrons are bound to move in 2D, as I said. You can take any number of arbitrary different combination of these materials and put them together in order to create a new Hamiltonian as you wish me to solve it experimentally in the lab by studying their electrical properties. And as I said, there are different kinds of materials available: semi-metals, superconductor, metal, insulator, semiconductor, etc., etc. And this list that I show here is non-exhaustive, and there are more materials available in different kinds. I mainly work with the graphene in the lab. So we have monolayer graphene, bilayer graphene, where it's naturally existing a layer of carbon atoms, as you can see here, in a hexagonal manner. And then there can be 2 layers of graphene. Also in our lab, we can twist 2 layers of graphene, where you can see that the single layer graphene from conical band structure to give something like a flat band, where the electrons are supposed to spend more time with each other, giving rise to different kinds of properties, which is not possible to get in a single layer graphene. So in the lab, we can take this single monolayer of graphene or bilayer of graphene, and I can twist one of them on the other and modify the band structure even from here to here, and study various phases of matter. And not only this, that we can do it with the graphene, we can also combine graphene with other materials, and that can give rise to various different kinds of possibilities in terms of Hamiltonian, if you may say so. So what you can do in the lab, and what we do in our lab, by the way, is that we make this kind of structures and make electrical FET, like field effect transistor-like devices out of it, and study their electronic property. Like each layer of graphene is definitely not superconductor, but if you take and twist them with each other, then eventually there are under certain condition, you can see even they behave like superconductor, while the next place is highly insulating. By just changing few electrons in the sheet, you can change from a highly conductive to a completely non-conductive state. And what are the things that you can do in the lab if you come to LQP? Well, you can prepare the substrate where we want to exfoliate and get these monolayers that we can assemble them. And then you can actually exfoliate them. So we just take the crystals and make copies on a Scotch tape, and then we press it on the substrate that we prepared, and that way we can get some single layers of different materials. And this is how we look at them using optical microscope or atomic force microscope and identify which are the ones that we can use. And then what we do, we take all those good materials and we use our small system in the lab where we put them together one after another, like we want to sandwich with each other to create a new Hamiltonian for us to study. And those stacks that we make in that machine, then we prepare and process, and then we take them to the Micro Nanotechnology Center and the CMI in EPFL, and we fabricate our devices, which are basically hall bars with a certain number of gates, which are nothing like a field effect transistor-like devices. And then we put it on in low temperature in helium-3, which, as you can see here, it's 250 millikelvin, which is, by the way, room temperature is 300 Kelvin. So you can understand this is the order of magnitude, 3 order of magnitude lower than the temperature that you are in. And then we have also another device, another fridge, which is a dilution refrigerator. We can go to even lower temperature, where we would take these topological states of matter and try to create topological quantum computers, like qubits that are topologically protected. And eventually we take those devices in these fridges, and then we measure, and then we do our data analysis and modeling. And if you will be coming to the lab, you can take part in any of this job that we said, and try to enjoy what we do in our lab. And at the end of the day, I would like to say that logic can only take you from A to Z, but if you can imagine, it can take you everywhere. Thank you so much.